All right, now in this video, we're also going to look at the epsilon-delta definition of the limit, but the limit that we're trying to prove here is now going to be nonlinear. And so it's going to make the algebra a little bit more complicated. It's going to make the proof a little bit more opaque, and it's definitely going to need us to do some preliminary work, make some additional assumptions in order to make this proof work out. Now, it should be noted that all nonlinear problems are going to have a similar kind of procedure that you're going to have to do. But they're all going to be a little bit different. So quadratic ones are going to do one thing, and square root ones or absolute value ones are going to do something a little bit different. And so just be aware. There's going to be a stage where I'll draw your attention to sort of where you have to apply a little bit of a trick in order to get it to work out. Okay, but let's look at this particular example. So we want to use the epsilon-delta definition of the limit to prove that the limit as x goes to 1 of x squared plus 4 is equal to 5. Now, as with the linear case, we have to use that definition of the limit where we want the difference between x minus c, if it's less than a delta, which is a small number, then we want to establish that the function and the difference between that and the limit at that point is going to also be less than epsilon, which is potentially a different small number. And the preliminary work we have to show is to sort of show the connection, working from the hard side, basically, to the easy side. And then the proof, we start with that if statement and work our way toward the then statement. And sort of taken by itself, some of these proofs can seem opaque because of the extra assumptions we have to make, and particularly as these problems get more complicated. So the work that we're going to do, essentially, again, similar to the previous linear examples, we're going to have to work essentially backwards to get the relationship we need. So we're going to start with the fact that x squared plus 4 minus the limit is less than epsilon. Close my parentheses right there. All right, so given that, if we simplify the expression inside the absolute value, we end up with this. And then keep in mind our x minus c in this case is x minus 1. So what I'm going to do here is I'm going to factor x minus 1, x plus 1, less than bar epsilon. And then we can, because they're multiplied together, we can split these into essentially the absolute value of x minus 1 times the absolute value of x plus 1 is less than epsilon. Now, what we need is we need to turn this x plus 1 into a constant. And for that purpose, we're going to think about being in the neighborhood of 1. So remember that delta and epsilon, they're both small numbers. So we can be very cautious about what we mean by small. We could pick some relationship, but I'm going to try to use whole numbers just to make the most sense, to be the most clear. So let's suppose we're within 1 unit of x equals 1, which is where our limit is approaching to. So we're on the interval 0, 2. So where is the expression x plus 1 the largest on this interval? And what is the value there? That's essentially the claim that we're going to make. So with it, once you get within 1, this x plus 1 expression can never be bigger than, and on this interval between 0 and 2, x plus 1 is the largest at x equals 2 and has the value 3. Now, everywhere else on that interval, x plus 1 is going to have a smaller value. So this is the maximum possible value that it can always have. Now, remember, we're dealing with inequalities here. So being less than something is fine. We don't need it to be equal. We just need it to be less. So the largest possible value, once you get within a decimal point less than 1 of x equals 1, once you're within that interval, then this x plus 1 factor is always going to be 3 or smaller. So we're going to suppose that on this, suppose that nearby x plus 1 is less than or equal, we'll just say less than 3. So inside this interval, technically you have open intervals, but it doesn't really matter. And therefore we replace that in the expression. So this expression is now going to imply that x minus 1 times 3 is also going to be less than epsilon. And therefore, the relationship that we want is that epsilon over 3 is going to be the value for our delta. When we work backwards. Well, when we work in the forward direction, in the if-then direction. And so now we actually follow the if-then statement and we go forward to show that if we start with the if, we can end with the then, but we're going to have to make certain assumptions. Last time we made the assumption about the relationship between epsilon and delta, but now we're also going to have to make this assumption about this x plus 1 factor. This is why it's going to look a little bit more opaque. Now, again, when you're working backwards, if you have a different kind of nonlinear problem, typically with absolute values, you run into less of an issue because you know which side of the absolute value you're on, and so you can rewrite your expression that way. But if you're dealing with things like square roots or things like that, this is the kind of analysis that you're trying to do. You're always trying to pull out the factor x minus c and then leave everything else to the one side. Now, again, it should be noted, if you've made any arithmetic mistakes, this is the stage at which you will notice it, because you won't be able to factor out your x minus c term. But different algebra tricks may be necessary in order to get that factor to come out. All right, now the if-then statement. So we say, suppose that x minus 1 is less than delta, which is some small number. And further, suppose that delta is equal to epsilon over 3. Then, there's our if, then there then. These are if statements. Then we can say that x minus 1 is less than epsilon over 3. And then again, the whole point of a proof is to reason about it, to argue about it. So you do need words. You can't just use algebra. But there is algebra involved. So now we're going to multiply both sides by 3. X minus 1 is less than epsilon. Now, here is where the sort of the trick, again, the second trick comes in. Now we want to say, so on an interval near x equals 1, like 0, 2, the expression x plus 1 is always less than 3. So we can rewrite our expression as x plus 1 x minus 1 less than epsilon. And this seems like, again, when you're going in the sort of if-then direction, this seems like an opaque, like, why would you do that? Why are you using x plus 1? Where did that come from? Well, it came from our backward analysis. It came from this step right here. But in the forward direction, we don't have that. We're working from that knowledge. And so now we have the information we need in order to put this into the form that we need in order to make our proof work. And you'll see this in a lot of proofs where there's like a step. It's like, why did you do that? How did you know to do that? The mystery is because they worked it out in a different order. And usually it's something that cancels. Okay, so then we get inside our absolute values, again, just to be completely clear about what we're doing here. And then we square them out, FOIL. And then we rewrite it in our function form, x squared plus 4 minus 5 is less than epsilon. Therefore, the limit of x squared plus 4 as x goes to 1 is equal to 5. And so that's our proof, QED.